Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the arithmetic instructions related to 8086 microprocessor under the course Microprocessor and Microcontrollers. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals, authors A.K. Ray and K.M. Gurchandi, publication Tata McGraw-Hill Education. So arithmetic instructions in 8086 processors are used to perform arithmetic operations like addition, subtraction, multiplication, division, etc. So the following are the instruction under this group. So for performing addition, we have the instruction add, ADC, add along with the carry, increment, INC, ASCII adjust after addition, AAA, decimal adjust after addition, DAA. These instructions we already discussed in the previous session. Next, the instructions to perform subtraction like SUB subtraction, SBB subtraction with borrow, decrement DEC, negate NEG, compare CMP, AAS ASCII adjust after subtraction, DAS decimal adjust after subtraction. These instructions also we have discussed in the previous session. Now we are going to see the left out arithmetic instructions related to multiplication and division and conversion of the data. So the instruction to perform multiplication, we have the various instructions are mul, multiplication, which is unsigned, whereas imul, which is for signed multiplication, AAM, which is ASCII adjust after multiplication. Next, instructions related to division operations are DIV, IDV, DIV, AAD, DIV unsigned division, IDIV signed division, AAD ASCII adjust before division. Next, instructions to conversion of data. One is CBW and CWD. CBW which is convert byte to word, whereas CWD is convert word to double word. So now we will see each and every instruction, the significance, syntax, as well as implicit operands and with examples. Mul, which is unsigned multiplication. Either we can multiply a byte or a word. In 8086 processor, we can go for multiplication, which is 8-bit by 8-bit or 16-bit by 16-bit multiplication. So the instruction multiplies an unsigned byte or word. One should be consist of either AL or AX. If it is 8-bit case, AL register. If it is AX register, that is for word case, it is in AX register. The unsigned byte or word may be in any one of the general purpose registers or memory locations. The most significant word of the result is stored in DX, while the least significant word will be stored in AX register. The immediate operand is not allowed in the instruction. All the flags are modified depending upon the result. If most significant byte or word of the result is 0, then a carry flag and overflow flag will be set. So now here for multiplication, two cases are possible. Either we can go for 8-bit by 8-bit multiplication or 16-bit by 16-bit multiplication. When we are doing 8-bit by 8-bit multiplication, one of the operand must be specified in AL register. The second operand will be specified in the instruction, either in the register or memory location. After multiplying 8-bit with 8-bit, the product is 16-bit. This 16-bit product we can find in AX register. Whereas in 16 cross 16, one of the data we have to place in AX register. Whereas the second operand we can specify either in the register or memory location. After multiplying a 16-bit data with a 16-bit data, the result is 32-bit size. In 8086 processor, we don't have any register of size 32-bit. So out of these 32 bits, the lower 16 bits we can see in AX register, the upper 16 bits we can see in DX register. The syntax of the instruction is, it is only single operand instruction, mul. Here we are going to be place OP1, where OP1 can be a register or memory location. Depending upon the size of OP1, either it can be 8-bit by 8 multiplication or 16-bit by 16 multiplication. So example, mul BH, which implies here BH is a 8-bit register. So BH register contents will be multiplied with AL register contents. The result we can see in AX register, which is 16-bit size. Next, mul CX. Here the register is 16-bit size. So the contents which are CX register will be multiplied with the 16-bit AX register. The 32-bit result we can see in AX DX register pair. The lower 16 bits in AX register and the upper 16 bits are in DX register. Next, mul. Here we are using word pointer. So whatever the location which you are considering, that is SI, this will be corresponding to memory location. So what is the size of data? The memory location contents which you are going to access is word. So this instruction, it is for a 16-bit multiplication. So the contents of SI memory location contents will be multiplied with AX and the result we can see in AX DX register pair. So one of the operand is memory location which is in SI register. The second operand in AX register. The result we can see in AX DX. The lower 16 bit in AX register, the upper 16 bits in DX register. Next we will see IMUL, which is for signed multiplication. For mul, IMUL, the functionality, syntax, constraints, everything is same. Only the difference is what kind of data we are going to use for multiplication. Either it is signed or unsigned. If it is unsigned, we use mul instruction. If it is signed, we use IMUL instruction. Remaining things are same as that of MUL instruction. So this instruction multiplies a signed byte or source which is operand by source byte which is in AL register or a signed word in source operand by a signed word which is in AX register. Here also either byte addition or word multiplication is possible. The source can be a general purpose register or memory operand, index register or base register, but it cannot be immediate data. So in case of 32-bit result, the higher order word, that is upper 16 bits, we can see in DX register and the lower order word which is lower 16 bits we can find in AX register. The auxiliary carry, parity flag, sign flag and zero flags are undefined after IMUL. So if AH and DX contains parts of 16 and 32-bit respectively, the CF carry flag and overflow flag will be set. The AL and AX register are implicit operand. For 8-bit multiplication AL, for 16-bit multiplication AX register are the implicit operand respectively. The unused higher order bits of the results are filled with sign bits and carry flag and auxiliary flag are cleared. Example, IMUL BH. So here the source operand is a 8-bit register. So in this case, the BH register contents will be multiplied with AL register contents and the result we can see in AX register. Next, IMUL CX. So here CX is a 16-bit register. It will be multiply with AX register contents, and the result we can see DX AX register pair. IMUL SI. Here pointer is not specified, so it may take 8 bits. So the SI register contents multiply with AL register, and the result we can find in AX register. If it is mentioned as word, then SI register contents will be multiplied with AX register contents, and the result we can see in DX AX register pair. So this is about multiplication for signed as well as unsigned. Next we will move to next instruction, which is AAM, which stands for ASCII adjust after multiplication. So this instruction, after executing, converts the product which is available in AL register into unpacked BCD format. So packed BCD format means each BCD number or digit will be represented with 4 bits, whereas in unpacked, each and every digit will be represented as 8 bits. So AAM instruction follows a multiplication instruction that multiplies two unpacked BCD operands, that is, higher nibble of the multiplication operand should be 0. The multiplication of such operands is carried out using mul instruction. Obviously, the result of multiplication is available in AX register. The following AAM instruction replaces the contents of AH registers by tens of the decimal multiplication and AL the singles of the decimal multiplication. So the product which is there in AL register, the least digit will be placed in AH register, AL register. The next digit is placed in AH register. So example, move AL comma 04. So AL is loaded with 04. Move AL comma 09. That is BL content is 09. Then we are given mul BL. Here BL is a 8 bit. So AL register contents will be multiplied with BL register contents. AL is 4 and BL is 9. 9 fours are 36. It is in decimal. But in the hexadecimal, the equivalent value is 24H. So the 24H will be exist in AHAL register, that is AX register contents. After AAM instruction, whatever the decimal equivalent is there, this will be copied into unpacked BCD, that is 06 and 0. 06 we can see in AL register, whereas 03 we can find in AH register. Now we will see the instructions related to division operation, which is unsigned division. This instruction performs unsigned division. For division, two possible cases are there. One is we can divide 16-bit data with 8-bit data, or 32-bit data with 16-bit data. Only these two are possible combinations. So it divides an unsigned word or double word by a 16-bit or 8-bit operand. So here the divisor can be 8-bit or 16-bit. If the divisor is 8-bit, the dividend is 16-bit. If the divisor is 16-bit, the dividend is 32-bit. The dividend must be in AX register if it is 16-bit case, and the divisor which is a 8-bit, this we can represent in any one of the addressing mode like register or memory. After division of a 16-bit by 8-bit, the result will contain quotient portion and remainder portion. Quotient will be there in AL register, remainder will be placed in AH register. If the result is too big to fit in AL register, then type 0, that is divide by 0, and interrupt is generated. Whereas in the case of 32-bit by 16-bit division, the 32-bit dividend will be placed in AX DX register pair, in which the lower 16 bits are in AX register, the upper 16 bits are in DX register. The divisor, which is 16-bit size, will be kept in any one of the register or memory location. So after division, the quotient we can find in AX register and the remainder is in DX register. The quotients we can find in AX and remainder in DX respectively. This instruction does not affect any flags. Syntax we can see example. First we'll write the syntax. So the syntax of the instruction is div operand 1, where the operand 1 can be a register or memory location. Example div bh. Now as the divisor is a 8-bit register which is bh, so this instruction will perform the 16-bit data by 8-bit data. 16-bit we have ax, this will be divided by bh. After this, the quotient we can see in AL register and the remainder is in AH register. The second example, div dx register. Here the dividend is 16-bit case. So dividend will become a 32-bit, which will have in AX register and DX register respectively for lower 16 bits AX, upper 16 bit DX register. The divisor which is 16 bit DX, so here it will be divided with DX register only. If you want to change this, it can be a BX register. Now we can divide with BX register. What are the operand we have specified, that will become divisor. So after this division operation, the quotient is in AX register, the remainder can be DX register. If I write div AX register, this instruction will do DX AX register divided by AX. If you have the instruction div DX register, these are allowed only. DX AX register pair will be divided by AX. For all these cases, the quotient and remainder will be same as that of 32-bit by 16-bit case. Here the operand can be a memory location also. The next instruction is IDIV, which is signed division. The instruction div and IDIV will differ with respect to what kind of data we are using for division operation. Remaining functionality constraints are same, where the operands we have to place, where we can find the result, that is same with respect to div. In IDIV, the data is signed division. So this instruction perform the same operation as div instruction, but the signed operands. The result are stored similarly in case of div instruction in both the cases of word and double word division. So if it is word division, that is 16-bit by 8-bit division. The second case is 32-bit by 8-bit division. We can find the quotient in AL register, remainder is in AH register. If it is 32-bit by 16-bit division, quotient we can find in AX register, the remainder can be in DX register. The result also will be the signed numbers. The operands are also specified the same way in div instruction. Divide by 0, interrupt is generated if the result is too big to fit in AX register, if it is 16-bit dividend operation, or AX DX register pair if it is 32-bit dividend operation. All the flags are undefined after IDIV instruction. The next instruction is AAD, which stands for ASCII adjust before division. The ASCII instructions which are like AAA, ASCII adjust after addition, AAS, which is ASCII adjust after subtraction, AAM, which is ASCII adjust after multiplication. These three arithmetic operations, addition, subtraction, multiplication, will be done after the instruction. Whereas for AAD, this will be done before division operation. The AAD instruction converts two unpacked BCD numbers in AHAL register to equivalent binary number in AL register. This adjustment must be made before dividing two unpacked BCD digit in AX by the unpacked BCD byte. So the parity flag, sign flag and zero flag are modified, while auxiliary carry, carry flag, overflow flag are undefined after the execution of AAD instruction. In this instruction queue sequence, this instruction appear before DIV instruction. So let us consider the AX register contains 0508. So 0508, which is a unpacked BCD number. First, this will be converted into packed BCD, that is 48D, which is 48 hexadecimal H, which is packed BCD number, decimal number, sorry, 58D. Before conversion into the register, however, the hexadecimal representation will be takes place. So 58, the hexadecimal is equivalent to 3A. This will be loaded into AL register. So the AAD results, AL register will contain 3AH. The result of AAD execution will be gives in the hexadecimal number 3A in AL and 00 in AH register. Note that the 3A is the hexadecimal equivalent of the decimal number 58. Now instruction DIV DH may be executed any instruction, so that ASCII adjust after division, it is ASCII before division operation. Usually we are going to take after operations, but only for division it will takes before division operation. All the ASCII adjust instructions are called as unpacked BCD arithmetic instructions. The next instructions are for conversion of the data. CBW. All these instructions for conversion CBW and CWD are zero operand instruction. It is a implicit operand. So this instruction, it is used for converting signed byte to word. So whatever the signed byte is there, this we have to load into AL register. The word after conversion we can see in AX register. This instruction converts a signed byte to a signed word. In other words, it copies the signed bit of the byte to be converted all the bits in the higher byte of the result word. The byte to be converted must be in AL register. The result after conversion we can see in AX register. It does not affect any flags. So before using this instruction, let us consider AL will have some binary format which is a 8-bit from B0 to B7. So after CBW, we don't specify any operand because it is a zero operand. Implicit operand is only AL. So after executing this, the result we can see in AX register. Out of this AX register, AL will contain the same data, that is from B0 to B7, whereas AH register, in each and every bit position, the B7 will be copied. In all the 8-bit positions of AH, B7 will be copied. The next instruction is corresponding to CWD, which is convert word to double word. Here also it is zero operand instruction. Whatever the data which is taking as signed data in AX register, which is signed word will be converted into double word, and the result we can see in DX AX register pair. So this instruction copies the signed bit of AX to all the bits of DX register. This operation is to be done before signed division operation. It does not affect any flags. So here, before executing CWD, the data we are going to be placed in AX register, which is of 16 bits, that is B0 to B15. Then we have to use CWD instruction. No operands are there. Implicit operand is AX. After executing this instruction, we have DX AX register pair, where AX will have the same contents, that is B0 to B15. Whereas for DX, each and every bit will be placed with the signed bit of AX register. Signed bit always will be there in the MSB position. So this MSB bit position will be copied into each and every position. The next category is flag manipulation and mission control instruction. These instructions control the functionality of the available hardware inside the processor chip. These are categorized into two types: flag manipulation instructions, mission control instructions. The flag manipulation instructions directly modify some of the flags of 8086. So in 8086, total we have 9 flags. Out of these 9 flags, only 3 flags we can change with respect to the instruction, like carry flag, direction flag, and interrupt flag. Only these are possible to change. The mission control instructions control the bus usage and execution. Now we will see first flag manipulation instructions and their functionality listed in the table below. First one is CLC, which is for clearing the carry flag. Before executing this instruction, the carry flag may be 0 or 1. So after executing this instruction, the carry flag will be cleared. Next one is CMC, which is complement the carry flag. Before executing this instruction, if the carry flag is 0, it will be complemented. If it is 1, it will be changed to 0. So here, after executing this instruction, the carry flag before the instruction, whatever the value is there, that will be complemented and it will be copied into carry flag. Next one is set carry flag. After executing this instruction, the carry flag is equivalent to 1. So these 3 instructions are used for manipulating the carry flag. The next instruction is CLD, which is for clear direction flag. So after executing this instruction, the direction flag will become 0. STD, which is for set the direction flag. So after executing this instruction, the direction flag will become 1. So these are the 2 instructions which we are having for altering the direction flag. So mainly for a string manipulation instruction, the direction flag will change the execution of the string manipulation instructions flow. So either we have to execute CLD or STD depending upon the construct. Next, CLI, which is a clear interrupt flag. This instruction, once you executed, the interrupt flag in the flag register will become 0. Set interrupt flag. Once you execute this instruction, the interrupt flag will be set. So these 2 instructions are related to interrupt flag. So out of 9 active flags in the 8086 processor, only 3 flags we can alter. One is carry flag, the second one is direction flag, third one is interrupt flag. Remaining flags we can't alter. So the instructions modify the carry flag, direction flag, and interrupt flag directly. The direction flag and interrupt flag, which may be modified using flag manipulation instructions, further control the processor operations like interrupt responses and auto increment or auto decrement modes. Thus, the respective instructions may also called as mission or processor control instructions also. The other flags can be modified using pushf or SAHF instructions, which are termed as data transfer instructions. No direct instructions are available for modifying the status flag except carry flag. Next, we have few more mission control instructions. The mission control instructions supported by 8086 are listed below. They do not require any operand. All are zero operand instruction. Wait, it is for wait for test pin goes to low. Halt, halt the processor. NOP, no operation. ESC, escape to the external device like NDP, numerical data processor, which is a coprocessor. Lock, this lock instruction is a prefix to any another instruction which is to lock the bus. Now we will see the detailed explanation for each and every instruction. So after executing the halt instruction, that is HLT, the processor enters into the halt state. Two ways to pull it out of the halt state are reset the processor or to interrupt the processor. The next one is NOP instruction. When NOP instruction is executed, the processor will not perform any operation till 4 clock pulses, except increments the instruction pointer by 1. It then continues with further execution after 4 cycles. Mainly these NOP instructions are used to provide a delay programs. There we are going to use NOP instruction. The next instruction is escape. So whenever we have a coprocessor system, then to switch from main processor to coprocessor, we use escape instruction. So the escape instruction, when executed, frees the bus for an external master like a coprocessor or a peripheral device, so that the bus can be accessed by the coprocessor. The next instruction is lock instruction. This lock instruction is a prefix to any another instruction, any instruction we can have. The lock instruction prefix may appear with another instruction. When it is executed, the bus access is not allowed for another master till the clock prefix instruction is executed completely. So when this instruction is executed, the bus access cannot be granted for any other device. This instruction is used in case of programming for multiprocess systems. The next instruction is wait instruction. The wait instruction, when executes, holds the operating process when the current status till the logic level in the test pin goes to low, where the test pin is a active low signal. So the process goes on injecting the wait stages in the instruction cycle till the test pin goes to 0. Once the test pin is 0, it continues further execution. So whenever for any cycle like a write operation or read operation, if more cycles are required, then the processor will enter into the wait states. So once the wait states are done, it will go for normal execution. So thank you. In this session, we have discussed a few instructions related to arithmetic operations, mainly related to multiplication, which is mul, imul, and ASCII adjust after multiplication. Next, we have discussed the instructions corresponding to the division operations, which are unsigned division DIV, signed division IDIV, and ASCII adjust before division operation, which is AAD. Next, to conversion of the data instructions CBW, convert byte to word. The second one is CWD, which is convert word to double word. The next category we have discussed is flag manipulation instructions and processor control instruction. Under processor control instructions and flag manipulation instructions, we have studied the few flags which are modified by using the instructions. 3 flags we can modify: carry, direction, and interrupt flag. So for carry flag, we can clear by using CLC instruction. We can set the carry flag by STC instruction. We can complement the carry flag by using CNC instruction. Similarly, for direction flag, either we can set direction flag or clear the direction flag. To clear the direction flag, CLD. For set the direction flag, STD. Similarly, for interrupt flag, either we can set or clear. Clear interrupt flag, that is CLI. Set interrupt flag, which is STI. Then we have discussed the processor control instructions like wait, which is to wait until test pin goes to low. Escape, to grant the bus access for the coprocessor. NOP, no operation. Halt, HLT. These are the instructions which are studied under processor control instructions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.